Put 5 evenly spaced dots on a circle, connect every second dot, and a perfect star appears with every crossing already locked to the golden ratio. Seriously, watch. Start at the top dot. Skip the next one. Draw a line to the one after it and repeat exactly that move. The line ricochets around the circle, returns to its starting point, and somehow we get 5 equal points, 5 equal inner angles, and a smaller pentagon sitting dead center. We never measured an angle. We never adjusted a crossing. The only instruction was skip one. And here's the part I want to hold back for a moment. Why does that tiny instruction control all of this? Why does the path close instead of getting stuck in a smaller loop? Why are the intersections placed at one very particular ratio? The answer is hiding in two completely different descriptions of the same drawing. One description lives on the circle and treats the dots like positions on a clock. The other lives inside one of these crossed lines and turns the star into a machine for making similar triangles. First, wreck the symmetry a little. Drag one dot away from its evenly spaced position while keeping the same connecting rule. The path still makes a star-shaped loop, sure, but the points become lopsided and the center pentagon slumps sideways. So 5 dots alone don't guarantee perfection. Equal spacing is doing real work. What is strange is how little work we need to describe it. Every neighboring pair is separated by exactly 1/5 of a turn. That fraction, 1/5, is about to run the entire drawing. We can erase the star, keep only the 5 dots, and rebuild the whole thing as arithmetic. 1/5 of a turn gives us a wonderfully small clock, 0, 1, 2, 3, 4, and then back to 0. Connecting neighboring dots would mean adding 1 each time. 0 to 1, 1 to 2, and around the outside we go. That produces the ordinary pentagon. The star uses +2. Start at 0, add 2 and land on 2. Add 2 indeed. Again, 6, which wraps around this 5-position clock to 1. Then 3, then 5 wraps to 0. So the visiting order is 0, 2, 4, 1, 3, 0. Every point gets visited exactly once before the line closes. That is already a clean answer to one mystery. The line doesn't choose its root by geometry. Its root is forced by counting modulo 5, meaning we throw away complete groups of 5 whenever we wrap around. And 5 has a useful stubbornness here. 2 and 5 share no smaller factor, so repeated jumps of 2 can't get trapped among only some of the dots. Try the same jump on 6 dots. 0, 2, 4, 0. Uh-oh. The other 3 dots never get touched. Starting at 1 makes a second triangle. The intended 6-pointed star splits into 2 separate loops because 2 and 6 share the factor 2. On 7 dots though, jumps of 2 visit all 7 positions. Jumps of 3 do too, and now 2 different star shapes are available. For 5 points, there's only one genuinely new connection rule after we ignore direction. Jump 1 gives the pentagon. Jump 2 gives the pentagram. Jump 3 traces that same pentagram backward, and jump 4 traces the outside backward. 5 is the first number where the skip rule can create a single closed star. Fine. That explains the route. It still hasn't explained the perfection of the angles, and that part drops straight out of the circle. The counting tells the line where to go. Equal arcs tell it exactly how to meet itself. Look at the star's top point and the 2 diagonals leaving it. They end at 2 lower dots. The top angle is an inscribed angle, so it measures half the arc between those endpoints that does not contain the top. That arc spans one gap between neighboring dots, 1/5 of a circle, or 72 degrees. Half is 36, so every sharp point of the star is 36 degrees. No protractor has entered the building. The circle measured for us. Now take a broad angle inside the central pentagon. The crossing lines around it form a triangle whose other 2 angles are star points, each 36 degrees. The remaining angle is 108 degrees, an interior angle of the central pentagon. Rotate the diagram 72 degrees and it lands on itself, so the calculation applies at every crossing. Equal arcs create equal chords, producing 5-fold rotational symmetry, and every part repeats. Pause on the finished figure. Its perfection isn't a lucky consequence discovered after drawing. Once the 5 arcs are equal, the chords have fixed lengths, and every angle between them is prescribed by the arcs they intercept. The skip 2 rule simply selects the longer chord 5 times. But the star does something the outer pentagon cannot. Its diagonals cross, dividing each other into long and short pieces. Their ratio appears in regular pentagons, spirals, certain recurrences, and a frankly unreasonable number of design books. Here it isn't decoration. The golden ratio is forced by the same 36-degree triangle. We can find it without coordinates, and the proof sits inside one point of the star. Take one point of the star, together with the horizontal diagonal cutting across beneath it. That makes an isosceles triangle with angles 36, 72, 72. Call each equal along side 1 and the base x. Now focus on the smaller triangle tucked beside it by a crossing diagonal. It has the same 3 angles, so the triangles are similar and their side lengths are scaled copies. This is where the drawing closes a trap on x. The large triangle's long side is 1, and its base is x. In the smaller triangle, the corresponding long side is x, while its base is the leftover piece of the original unit side, 1 minus x. Similarity gives 1 over x equals x over 1 minus x. Multiply through x squared equals 1 minus x, or x squared plus x equals 1. The positive solution is the square root of 5 minus 1, all over 2, about 0.618. Its reciprocal is 1.618, the golden ratio, phi. So a full diagonal divided by a pentagon side is phi. A long diagonal segment divided by its shorter neighboring piece is also phi. The ratio repeats because the triangle repeats. Okay, this is the good part. The golden ratio appears because the star contains a smaller copy of its essential triangle. Similarity demands a scale factor that survives being split into one whole part and one leftover part. Phi can do that, and it doesn't stop there. The crossings create a regular pentagon in the middle. Connect every second corner and another pentagram appears, perfectly aligned with the first, then another. The 5-point rule has built a geometric recursion. That inner pentagram is a scaled version of the original, so the entire argument starts over without changing a word. Its points are 36 degrees, its diagonals divide in the golden ratio, and its center contains another regular pentagon, ready to hold another star. If the outer diagonal has length 1, corresponding diagonals shrink inward by a fixed factor related to phi. Areas shrink by its square. The shapes never run out, they only become too small to draw. Every new crossing is determined by the first 5 dots. Here is the reversal. The star first looked more complicated than the pentagon, with its crossings and extra regions. Now those crossings reveal the simpler repeating rule. Each layer applies the same 5-fold symmetry again. 3 transformations make this precise. Rotate by 72 degrees and each layer maps to itself. Reflect across a line through any star point in its half swap. Scale around the common center by the inner to outer ratio, and one layer maps to the next. Rotation explains the 5 identical arms, reflection their matching sides, and scaling the infinite nesting. 3 motions account for nearly everything your eye calls perfect. A limit also hides at the center. Pick one corner from each nested pentagon. The corners march inward, turning and shrinking by fixed amounts. They form a discrete spiral toward the center. The infinite construction has a destination, though no finite layer reaches it, so the golden ratio wasn't an isolated numerical surprise. It controls the star's depth. But 5 now looks almost magical, and we should be suspicious. Place other numbers of equally spaced points on the circle and use the same skip rule, which make one star, which split apart, and which contain smaller copies of themselves. The arithmetic from earlier answers the first question immediately. With n points in a jump of k, the path visits every point exactly when n and k have greatest common divisor 1. If they share a factor, the drawing splits into that many loops. 8 points with a jump of 2 give 2 squares. A jump of 3 gives one sharp 8-pointed star. 9 with a jump of 3 makes 3 triangles. 10 with a jump of 4 makes 2 pentagrams. The 5-point star returning twice, woven through 10 points. These are regular star polygons, written as n over k in braces, n points, jump k. The pentagram is 5 over 2. The notation stores the instruction instead of naming every shape. 5 has a special economy. 3 points give a triangle. 4 with a skip of 2 bounce between opposite corners, never forming one connected star. At 5, the first non-neighbor jump is 2, coprime to 5. So the earliest regular star arrives all at once, connected, symmetric, and self-intersecting. Its crossing geometry is unusually tight. Each diagonal is divided by others in the golden ratio, and the center is another regular pentagon. 7-pointed jump 2 and jump 3 stars have richer angles and several kinds of internal regions. Beautiful, yes, but less visually blunt. The pentagram points at its own smaller pentagon and refuses to be subtle about it. Now we can answer almost everything. Equal spacing, forces equal arcs. The jump rule becomes modular addition. Coppermality keeps the path in one piece. Circle geometry fixes the angles. Similar triangles force phi. One loose end remains. How much can we disturb the original 5 dots before the star stops being perfect, and which pieces survive? Remove 1 dot and the modular route survives. We still visit the points in the order 0, 2, 4, 1, 3. Connectivity cares only about the labels in the jump. But the perfect angles disappear because the arcs are unequal. Rotate all 5 dots together and nothing changes internally. Enlarge the circle and every length scales while angles and ratios stay fixed. Shift the construction elsewhere and the star remains the same star. Equal spacing survives. Only position, orientation, or size changes. Now keep 5 points on one circle but space them unevenly. Each point angle is still half an intercepted arc, so the circle theorem survives. The angles stop agreeing because the arcs differ. The star stays cyclic and the root stays closed, but regularity and the repeated golden ratio vanish. Each assumption has a specific job. Here is the full answer. 5 equally spaced points carry 72-degree rotational symmetry. Skipping 1 point means repeatedly adding 2 modulo 5, visiting every position before returning. The chosen chords are congruent, their endpoint angles are 36 degrees, and their crossings create similar 36-72-72 triangles. Those triangles fit together with the golden ratio. The inner pentagon inherits the original symmetry, so the construction repeats forever. I love how little choice the drawing gets. Once the dots are fixed, the star cannot improvise. Its root, angles, crossings, proportions, and smaller copy all follow from one jump around a 5-position clock. Run the opening construction again. 5 dots. Skip 1. Keep going. Now the star does not appear like a trick. You can see arithmetic pushing the line forward, the circle setting each angle, and the smaller pentagon waiting at the center before the first diagonal reaches it.